You are probably overcomplicating vectors. The exam really only tests a few key ideas. So in this video, we're going to look at the most important types of vector questions you need to know for Cambridge 9709 paper 3. First concept that they test is finding the unit vector. So in this question, they've asked us to find a unit vector in the direction of L. Now, L is a line and its equation I've rewritten over here just for you. Now, the direction of L is always represented by this portion of the equation. This is the direction of L. So basically, if you have a line L, this direction portion is a line parallel to it, parallel to L. So this is negative I plus j plus 2k, right? So it represents the direction of L. And in general, if you want to find a unit vector of a vector, so let's say you have a vector AB. If you want to find its unit vector, you take the vector AB and divide it by its magnitude or modulus. And how do we find the magnitude of AB? So if AB is AI plus BJ plus CK, then its modulus is the square root of the squares of A, B, and C added together. Right? So applying this to our direction vector, which is minus I plus j plus 2k, we are going to divide it by its modulus, which is root of negative 1 the whole squared plus 1 squared plus 2 squared. So that gives us negative I plus j plus 2k by root 6. So we just write, we don't need to actually separate it out unless they ask us to. So 1 by root 6, the whole into minus I plus j plus 2k is the unit vector in the direction of L. Next concept that they like to test is finding the vector equation of a line. Now, a vector equation of a line is different from finding a vector. So a vector is something such as vector AB or vector CD. But the vector equation of a line is represented as R is equal to A plus lambda B minus A. Here, A and B are position vectors of 2 points on the line. Okay, so let's say you have your line M. There are 2 points on it, A and B. The position vectors have been given to us. So OA is negative 2i plus 2j minus k, and OB is 3i minus j plus k. So both the position vectors are given to us. To find the vector equation of a line, we just plug it in into the equation. So R is equal to OA plus lambda OB minus OA. I'm going to write them in matrix form. So positive 2 and negative 1 plus lambda. OB is 3 minus 1, 1 and minus OA. So minus of minus 2, minus of 2 and minus of minus 1. So we have R is equal to negative 2, 2 and negative 1 plus lambda 5, negative 3 and 2. This is the vector equation of line M. Concept 3 is checking whether two lines are parallel, intersect, or skew. Now, we actually just check if they're parallel or intersect, and if they are neither, then by default they are skew. So the first test that we do is checking whether two lines are parallel. How do we do that? So the test for parallel vectors is that they should be multiples of each other. Now, we don't test the entire two vectors. What we do is we do a short version of it, which is take the direction portion of each of the vectors. Now, the direction portion of the vector is the part of it that comes after lambda or mu. So I have written down both the vector equations here, and you can see I've marked it in red, the direction portions of each of the vectors. So we only use that portion to test for whether they are parallel. So what do? We just write them down. So -1, 1, 2, and 5, -3, 2. Now, for parallel vectors, one of the vectors or any of the vectors has to be some multiple of the other vector. So if one of the vectors is A and the other one is B, then it has to be a multiple. So this K could be anything. It could be a fraction. It could be a negative value. It could be positive. It can be anything, but it should apply to all three rows of the two vectors. So in this case, if from -5 I had to get 5, I would have to multiply this by -5. But if I multiply 1 by -5, I get -5 and not -3. Therefore, this is -1, 1, and 2 is not a multiple of 5 minus 3 and 2. So you write it like this, is not equal to k times 5 minus 3 and 2, and that's your proof that it's not parallel. So next we're going to check whether they intersect. I'm just erasing this so that we have some space to work on. Right, so when we want to check if two lines, two vector equations are intersecting, what we do, so if these are the two lines L and M, if they intersect, they have a common point. Now that common point is R, because R represents any point on the two lines. So if the two lines have a common point, that point is R, and therefore we just equate the two vectors. So -1, -2, -3, sorry, +1, -2, -3, plus lambda, -1, 1, and 2. We equate it to the other vector equation, which is -2 to -1 plus mu 5, -3, and 2. Right. Now we write down the parametric equations. So what are the parametric equations? Every row forms one equation and then we solve them simultaneously. So the first row is 1 plus, 1 minus lambda is equal to -2 plus 5 mu. If I neaten that out, I get negative lambda, -5 mu is equal to -3. That's the first of my equations. Now I take the second row, so negative 2 plus lambda is equal to 2 minus 3 mu. If I neaten that out, I get lambda plus 3 mu is equal to 4. Okay, I'm writing it like this, in this form, lambda plus mu and so on, so that I can plug it easily into my calculator. So I'm just going to do that now. So my calculator tells me that the value of lambda is 11 by 2 and that of mu is negative 1 by 2. Now what do? We need to find lambda, a lambda value and a mu value that works for all three lines of the equation. So you want to plug it into the third parametric equation. So negative 3 plus 2 lambda is equal to negative 1 plus 2 mu. If I plug in lambda is equal to 11 by 2, I get minus 3 plus 2 into 11 by 2, which is 11 minus 3, which is 8 for the left side. The right side is negative 1 plus 2 into mu, which is negative half. Cancel that out. So this is negative 2. So 8 is obviously not equal to negative 2. Therefore, lines are not intersect. Right? If they were intersecting, a lambda value would work for all three lines and so would the mu. So finally we come to the conclusion that if it's neither parallel nor intersecting, it must be skew. So the lines are skew. Next, they like to test whether you know that perpendicular lines have a dot product of 0. So here's a question. It says there are two lines L and M, and they've given us the vector equations of both the lines. Show that L and M are perpendicular. So to do this, once again, for perpendicular, parallel, angles, all of those, we use the direction portion of the equation. So I've marked them here. So the dot product of these two, that is 4i minus j plus 3k dot minus I plus 2j plus 2k, we have to show that it's equal to 0. How do you do a dot product? You multiply the coefficients of I, so 4 into minus 1, add it to the product of the coefficients of j, so negative 1 into 2 plus the product of the coefficients of k, so 3 into 2. And that gives us negative 4, negative 2, plus 6, which is 0. And that's the proof that the lines are perpendicular. The fifth concept that they test is whether you know how to find the point of intersection of two lines. So here I'm explaining this again. So if there are two lines L and M, so this is L and this is M, if they intersect, they have a common point R, because R in these two equations represents any point on the line. So there is a common point, so we can equate the R's. I'm writing it in matrix form, so 3, 2, 5, this is for L, plus S times 4 minus 1, 3, should then be equal to, if they intersect, it should be equal to 1 minus 1 minus 2 I'm writing m also in matrix form, plus t times minus 1, 2, and 2. Right, now we have to find, to show that they intersect, we have to find an S and a T that satisfies all 3 rows of the equation. So first we take the first 2 rows. So 3 plus 4s is equal to 1 minus t. We neaten that up to make it ready for inputting into the calculator. So 4s plus t is equal to negative 2. That's our first equation. And then 2 minus s is equal to minus 1 plus 2t. Neaten the second equation up to give us negative s, sorry, let me erase that, minus negative s, negative 2t is equal to negative 3. That's the second equation. And then we plug both of these into our calculators to find the values of s and t. So let me just do that. Using the calculator, I get s is equal to minus 1 and t is equal to 2. Now we have to show that this value of s and the value of t have to work on the third row as well. So 5 plus s into 3, so 3 into minus 1 is equal to minus 2 plus t into 2. So that gives us 5 minus 3 on the left side and negative 2 plus 4 on the right hand side. So 2 is equal to 2. This is true. Therefore, the lines intersect. Because we have found a value of s and that of t that is that works for all 3 rows of the equation. Now the second part of the question says, state the position vector of the point of intersection. So we know that the point of intersection is R, like I've marked it here. So you can use either the value of S or the value of T, plug it into one of these equations, either L or M, and that will give us the point of intersection. So that's what I'm going to do now. I'm going to take the value of, I'm going to use the equation of M. So T, R is equal to I minus j minus 2k plus t, which is 2, minus I plus 2j plus 2k. And that gives me I minus j minus 2k minus 2i plus 4j plus 4k. Gather the like terms and we end up with I minus 2i is negative I, negative j and 4j is 3j, and negative 2k plus 4k is positive 2k. That is the position vector of the point of intersection of the 2 lines. The next 3 concepts are usually intertwined. So we're going to go through them one by one using the same example. So here I've taken a question from the past paper which says that points A and B have position vectors as given in the question. And there's a line L that has an equation also given in the question. We are supposed to find the position vector of the foot of the perpendicular from A to L. I'm just going to draw that to demonstrate. So you have a line L and you have a point A whose position vector is given to us right here. So since the position vector is I plus 2j minus 2k, the coordinates of A are also known to us, which is 1, comma 2, comma minus 2. Okay, so from the point A, you have to draw perpendicular to the line L, and the foot of this perpendicular, that point, we're going to name it, let's name it N. Okay, and we are supposed to find the position vector of the foot of the perpendicular. That means we are required to find ON. All right, so in order to do this, we start like this. So we'll be using the dot product of AN and the line L and equating it to 0 because they are perpendicular. But to get to that point, the first step is always to name the foot of the perpendicular, which we've already done. And then, since N lies on the line L, ON is equal to R, because R represents any point on the line L. So this R here represents any point, the position vector of any point on the line, and N happens to be a point on the line. So ON is equal to R. So I'm going to just write that out. I'm going to write it in matrix form. So 1 minus 1, 3 plus mu 2 minus 3, 4. Right, so now we have ON, but they require us to figure out the value of mu. So in order to do that, the next step is to find AN. So AN is the line perpendicular to the given line L. And I think you might know that in order to find AN, we do ON minus OA. That's how you represent a vector in terms of its of the position vectors of its start and end points. Right. So ON, we've just written it down here. I'm going to shorten it even further and write it as 1 plus 2 mu minus 1 minus 3 mu and 3 plus 4 mu minus OA, which is given to us right here, and that is 1, 2 minus 2. Okay, it's just easier to work with them when they are written in this form. So now I'm going to shorten it even further. So 1 plus 2 mu minus 1, which gives me 2 mu. Then minus 1 and minus 2 gives me negative 3 and negative 3 mu. And 3 minus and minus is plus. So 3 plus 2 is 5, plus 5 and 4 mu. This is AN. I'm just going to check that. So 2 mu minus 3 mu and 2 plus 3, 5. Yeah, that's correct. Fine. So now we have represented ON in terms of mu. We've represented AN in terms of mu. Now, the one property that we can use here is that AN is perpendicular to the line L, which means their dot product is 0, right? So we're going to do AN, its dot product with the line L. So when we do the dot product with the line L, this is super important. Don't use the entire equation of the line L. Use only the direction portion. That's this. Okay, you don't have to use the entire R is equal to I minus J plus 3K and so on. Just use this portion because this represents the direction of L. So that is 2 minus 3 and 4. So the dot product of 2, minus 3 and 4 with an is 0 because they are known to be perpendicular. I'm going to rewrite that. So an we found was 2 mu minus 3 mu minus 3 and 4 mu plus 5 dot 2 minus 3 and 4 is equal to 0. Now all we have to do is solve for mu. So carry out the dot product. So how do we do that? Multiply the first row. So 2 into mu into 2. Add it to the second row. That is negative 3 into negative 3 mu minus 3. So that is, okay, I'm just going to write that as negative 3 into negative 3 mu negative 3 plus 4 into 4 mu plus 5 is equal to 0. So that is the dot product. Now we're going to simplify it further. So 4 mu plus 9 mu plus 9 plus 16 mu plus 20 is equal to 0. So gather all the mu's. So 9 and 16 is 25 plus 4 is 29 mu. And the remaining terms you're going to carry to the other side, it's minus 29. So that gives us mu as negative 1. So now that we know that mu is negative 1, we can plug that value back into ON. So remember, our task was to find the position vector of the foot of the perpendicular. So we had to find ON. So we put that value of mu, which is negative 1, back into this equation here. So we get 1 minus 1 and 3, negative 1, 2, negative 3 and 4. We simplify that out, you get 1, negative 2, which is negative 1, minus 1 plus 3, that is 2, and 3 minus 4, that's negative 1. This is ON. So that brings us to the next concept that they like to test, which is kind of related to this, which is finding the perpendicular distance from a point to a line. So in this case, the perpendicular distance from the point A to the line L is the distance AN. Okay, so how do we find AN? First, we find the vector AN. So we have already found that AN is equal to 2 mu minus 3 mu minus 3, 4 mu plus 5. Now we already know the value of mu is negative 1. So plug that in there. So 2 into negative 1 minus 3 into negative 1 minus 3 and 4 into negative 1 plus 5. Simplify that. So we have negative 2. 3 minus 3 is 0. And negative 4 plus 5 is 1. Right, so this is AN. Once you know AN, all you have to do is find its magnitude. So the magnitude of AN is the distance from the point, the perpendicular distance from the point to the line. The magnitude of AN would be root of negative 2 whole squared plus 0 plus 1 squared, which is root 5. And finally, the last of the concepts that they like to test is finding the reflection of a point in a line. So this is actually a bit of coordinometry. So just redrawing that, if you have your point A, your line L, you already have your perpendicular with the base of the perpendicular named as N. The reflection of A in the line L would be, if you extend it an equal distance on the other side of L, that would be the reflection. Now we already know the coordinate, we know the position vector of N, we know ON, right? ON was -2, 2 and -1. -2, 2 and -1. We already know A because that was given to us. So the position vector was 1, 2 and -2. To a -2. And we just have to find A dash. So let's say A dash's coordinates are X, Y, and Z. Right, so then we just use the midpoint formula in coordinate geometry, which says that the midpoint between two points is x1 plus x2 by 2 and y1 plus y2 by 2. Right, so in this case our -2 here is the corresponding coordinates of A and A dash. So 1 plus x by 2, which implies that x is -4, -1, which is -5. Similarly, we can do the y coordinate and the z coordinate. So 2 is equal to, this 2 is equal to 2 plus y by 2, which implies that y is 4 minus 2, which is 2. And finally, to find z, -1 is equal to -2 plus z by 2, which implies that z is -2 plus 2, which is 0. So the coordinates of A dash are -5, 2 and 0. And if they want you to write down the position vector of that point, that's OA dash. We just have to write the coordinates in vector form. So -5i plus 2j and 0k we don't have to write. So these are some of the key vector question types you should be familiar with for Cambridge 9709 paper 3. If you can recognize these quickly and apply the right method, you can secure a lot of marks on paper 3.